This lesson will discuss section 9.4, which is the common logarithm. At the beginning of this chapter, I mentioned that there were two specific logarithms that we were going to discuss, namely the common logarithm and the natural logarithm, that show up a lot in application. So the common logarithm is just simply written as log of x. There's no base because the base is understood to be 10. So this is really just log base 10 of x. This button does show up on your calculator. It is right here, log, L-O-G. And the anti-logarithm, which is the next definition, is this 10 to the x, which is also on your calculator. So the anti-logarithm is simply 10 to the x, and it only applies for the common logarithm. So since it's base 10, a lot of times this is a little bit easier. It's just kind of a matter of counting zeros. And so we can apply the properties that we learned in the previous section, plus the fact that we know this is base 10, to simplify and solve some of these logarithms. And in examples 30 and on, you'll see that sometimes you actually want to use the calculator to find some of these decimal approximations. So let's start off with something that has a nice clean number. If we want to take the common logarithm of the common logarithm of 100 to the 10,000. Well, first we are going to simplify this so that we use the properties of logarithms that we learned in the last section, and we bring that exponent down. So we end up with the log of 10,000 times the log of 100. And now this log of 100, since this is base 10, we say, okay, what do we raise 10 to? What power will give us 100? Well, in this case, that would be 2. You would square 10 to get 100. So this simplifies to be log of 10,000 times 2. Now, again, we can split this up based on the properties of logarithms, and we can say, okay, well, if we have multiplication inside, that's addition outside, so this would be log of 10,000 times the log of 2. Now the log of 10,000, again, we can say, okay, what exponent would we raise 10 to get 10,000? And essentially it's just a matter of counting the zeros, 1, 2, 3, 4. So this ends up being 4. And the log of 2 we just simply leave as the log of 2. You can find the decimal approximation for it, or you can leave it as such. So that's one where we can just kind of use the fact that we have these powers of 10 to simplify. Now if we go on to some of these other examples, we're going to need to use the calculator. For instance, if we want to find the common logarithm of 68.1, so luckily we have the calculator. Before this we had to use tables. If we go to our calculator, all we simply have to do is pretty much type it in as we see it, log of 68.1. So we hit our log button and then 68.1. Close the parentheses and hit enter, and it'll tell you that your exponent would have been 1.833. So log of 68.1 is going to be 1.833. And in this case I said to round to 4 digits, so there are 4 digits there. I want you to pause the video here for a second and try the next example. So for this example we end up with negative 1.585, and it makes sense for this example to have a negative exponent because we ended up with a small decimal here. So 10 raised to a negative exponent would give us this decimal 0.026. We can work the other way with this. We can say, okay, for instance, if we have log of some number and we know that instead the exponent here is 1.4048, well then we just need to use the anti-logarithm, namely 10 to the 1.4048. Again, if we plug that in the calculator, we have to hit second and then 10 to the x if we want to use that. We can do 1.4048. Close the parentheses, and you end up with 25.398. You could also just simply put in 10 and then use the caret button, and then 1.4048, and you'll end up with the same number either way. So if we round to 4 digits, this would be 25.40. I want you to pause the video here and try example 33. So for this example, you end up with 0.00183, and I included the 183 because we wanted 4 significant digits, and the first 3 zeros don't count as significant. We can do some more examples here. I do want people to be careful here. You cannot divide within the logarithm like this. You have to separate it out. You can't do the 685 divided by 6, not that that would simplify nicely anyway, but you have to do log of 685 divided by log of 6. We can't use our properties in this case because it's division outside of the logarithm. So we would just put it in exactly how we see here. We would say parentheses log of 685, close the parentheses twice, and then divided by parentheses log of 6, and close the parentheses twice. And we end up with 3.644. For example 35, in this case we do actually have the division inside, so if we wanted to, we could split this up to be the log of 16.5 minus the log of 2.7, and I'm going to show you here how either way we use this, we end up with the same thing. If we keep it as is and we take the log of 16.5 divided by 2.7 and then close the parentheses, we get 0.7861. If we split it up instead and do the logarithm of 16.5, close parentheses, minus the logarithm of 2.7, close parentheses, we end up with that same number. So either way you work through this one, this shows that the properties do work out. You end up with 0.7861. The next few examples are going to deal with some applications of these common logarithms. So one such case where this is applicable is in chemistry. Whenever you deal with pH, which is the hydrogen potential of a solution, it measures essentially the acidity of the solution. And pH is actually defined as the negative common logarithm of the number of hydrogen ions. And like I said, H plus here is the numerical value for the concentration of hydrogen ions in moles per liter. So water is said to have a pH of 7. It's supposed to if it's completely neutral with nothing else dissolved in it. Acids have a pH value between 0 and 7 depending on how acidic. 0 is extremely acidic, 7 is neutral. And bases have pH values from 7 to 14. And again, 7 is neutral, 14 would be extremely basic. For beer, the number of hydrogen ions is 6.3 times 10 to the negative 5th moles per liter, and we want to find the pH value of this liquid. So if we plug this in, we want to find that your pH is equal to negative log of 6.3 times 10 to the negative 5th, and we don't need to keep the units in here because it's understood to be moles per liter. So again, if we go to our calculator here, we hit negative log of 6.3, and this is your option here. Usually when we see times 10 to the, this is scientific notation, we use this button here that says EE, and we just put in the exponent. This is one way you can do it. You end up with 4.2. Likewise, you could end up instead saying that this is negative log of 6.3 times, if you hit this then, 10 to the negative 5th you'll end up with the same thing, 4.2. So in this case, we end up with a pH of 4.2, which in this case says that this is actually acidic. One thing to be careful of, it seems like this is, halfway between 0 and 7, so it would be very acidic, but again, this is a log-based scale, so if you remember the graphs of logarithms, they grow slowly. So just because this is 4.2, it's kind of away from the 7, it doesn't mean that it's extremely acidic, it just means it has some potential for acidity. So similarly, there's a couple other examples we have here. The intensity level of sound is given by the formula beta is equal to 10 times the log of I over I naught. Beta is the intensity level in decibels. The sound intensity I measured in watts per square centimeter, and I naught is the intensity threshold of hearing, which is a constant 10 to the negative 16 watts per square centimeters. So if we know that the intensity of the actual sound being produced is 10 to the negative 14th watts per centimeter squared, we want to find the decibel level. So for anybody interested in music, this would be an application of the logarithm. So in this case, we want beta is equal to 10 times the logarithm of, in this case, I is 10 to the negative 14th, and I naught is 10 to the negative 16th. So in this case, you could simplify before plugging in. We've got 10 to the negative 14th divided by 10 to the negative 16th. We can simplify that. You got negative 14 minus negative 16. So you end up with 10 squared. Again, negative 14 minus negative 16 will give you a positive 2. And in this case, we don't even really need to go to the calculator, because this is log base 10 again, and we want to know what you would raise 10 to get 10 squared. Well, you would raise it to the 2 power. It's giving you that exponent there. This also goes back to that property that we talked about. If you've got log of a base and then that base is present inside, all you really end up with is the exponent. So in this case, we end up with 10 times 2, which is 20, and we always want to make sure we remember our units. In this case, it is decibels. Very similar problem here. In this case, we've got power gain and loss of an amplifier or other electronic device. I want you to pause the video here and try this example, and then resume the video to see if you have the correct answer. So for this example, you should have found for the first part that the power gain was 13.8 watts, which makes sense considering the input was half a watt and the output was 12 watts. So we had an increase or a gain of 13.8. For part B, we ended up with a negative 0.792. Again, this would be a loss because we were having an input of 1.2 and an output of 1. So there was a decrease there, leading us to having a negative exponent. So this concludes the video for 9.4. Please go online now and complete your homework for this section.